In this video, we're going to talk about the definition of a function and also how that plays out with different types of functions. So the definition of a function is that it's a special type of relation where each input has exactly one output. The best way to start to wrap your brain around what that definition means is to look at some examples. So here I have two mapping diagrams. The first one is a function and the second one is not a function. So again, our criteria is this important statement here. Each input has exactly one output. In this first example, our domain is the set of all inputs and our range is the set of all outputs. So if we look at the elements in our domain, one element is 1 and it has exactly one output of a -1. Another element is 2. It has exactly one element. It's the same one that 1 has, but they still just have 1. And then the last element here is 3, and it has exactly one output of 6. When we look at what's not a function, here I'm going to start with 3. 3 has exactly one output, so it's not the problem child. But if you look at 2, it's going to 2 different outputs. And that right there is what makes the whole thing not qualify as a function. One way I like to think of determining that whether or not it's a function is that we like the input of a function to be predictable. So when I put something into a function, there is one and only one place where it is going to go. I like it to be predictable. So if you look here at this first function, when I put a 3 in, it's predictable that I'm going to get a 6 out. As soon as I put a 3 in, I know exactly where it's headed. However, in the second function, when I put a 2 in, it may come out as a 3 or it may come out as a -5. It's not predictable. It's more like a gamble. So you can think of a function as something like a Coke machine. When you push the Sprite button, you know you're going to get a Sprite out, unless someone with a sense of humor loaded the machine. And you can think of something that's not a function, like a slot machine. When you pull that lever, you don't know what you're going to get. It's a gamble. So that's the idea of each input going to only one output. It means once we decide on the input, we have a predictable outcome from there. No question about it. So that's what it looks like with bubble diagrams. Let's look at it, or I'm sorry, with mapping diagrams. I call them bubble diagrams sometimes too because they look like bubbles. Now let's look at it just with list of ordered pairs and see how it works out with that. Alright, so here we have a couple examples that ask us if the following is a function. And what we have here is we have our set notation brackets. And then we have, for this first one, we have a set of 4 distinct ordered pairs. Now this is giving kind of the same information as the bubble diagram, as the mapping diagram. As a matter of fact, you can decompose this into a mapping. So here, our domain is made up of all the x values. Our x values are 1, -3, 2, and 6. So I can list those out in my mapping diagram in the domain bubble. 1, -3, 2, and 6. And then my range is the set of all my y values. So that's going to be a -5, a -5, a 1, and a -2. So when we list those out, we do not need to repeat the -5. As a matter of fact, we don't want to repeat the -5. And then a 1 and a -2. Repeating the repeated values will keep it from revealing whether or not it's a function or not. And then we draw out the correspondence by putting an arrow between the two that are matched in an ordered pair. So my first ordered pair is 1, -5. So that means 1 goes to -5. My second ordered pair is -3, -5, so that means -3 also goes to -5. That does not mean it's not a function. 1 and -3 are still predictable. They can share an output. That is fine. 2, 1, the order pair 2, 1 tells me that 2 goes to 1. And the order pair 6, -2 tells me that 6 goes to -2. So each of my inputs are going to one and only one output. So this guy is a function. Sometimes I may ask you to explain why, in which case a good why answer would be to say that each input goes to only one output. Alright, so we'll look at the next example and see if that's a function or not. And I'll go ahead and break it down into the mapping diagram. You don't have to do that as a part of your work. I'm just doing it so you can see the correspondence between the two. So I'll just start by drawing my domain and range bubbles. Domain, oh, that's a B. Domain and range. And then we're going to list the input values. Here are input values. We have a 1 and a -3. So put in a 1 and a -3. The next one here is a 1 again, and I don't want to list that again. I've already got 1 listed, so we'll just go with that. And then the last one here is a 6. Then with the range, we have a -5, we have that twice, a 6 and a -2. So it's always good after you do that, make sure that there are not any repeats within any given bubble. And then with our order pairs, we have the 1, it's going to go to a -5. The -3 will go to the -5 as well. The 1, so the 1 we already have is going to go down here to the 6. Curve it a little. And then the 6 will go to a -2. And here we want to make sure that's a 6 of the domain going to a -2 of the range. We wouldn't use the 6 over here in the range for that. Okay, so that's what we have. Now this is not a function, so I can tell you that. But the reason why we have a 1 going to a -5 and a 6, but we also have 1 and -3 going to -5. So this kind of really is testing if we understand which one of those is the issue. Going back to it being predictable, the one that makes an issue with predictability is the one going to two different places. Okay, the 1 is going to a -5 and it's going to a -6, so it's kind of a gamble which output you're going to get. So that is the reason why it's not a function. So if we needed to state our why on that, we could say it's not a function because 1 goes to -5 and 6. And that really hammers home that you understand what is the issue here and not just that it's not a function or it is a function. Alright, so here I have a couple graphs. The first one is just a basic linear function. It is a function. And then the second one we have an example of something that's not a function. Now, the definition still holds true. Each input going to only one output. And remember, your inputs are always your x values, and we read those off of the, or whatever your deep independent variable is, but it's always on the horizontal axis. And then your output is always going to be on the y-axis. In this case, they're y's. The letter can change, but the output is always on the vertical axis. Okay, so now to see that for a line that each input goes to only one output is just take into consideration one point on this graph. So there's a point. Now its x value would be a 3, and its y value would be a 3. So it only has one y value for that point. And as I move up and down the line, like let's say I come down here, then it would be 1, my output would be 1. And no matter where I move up or down that line, I'm going to have one y value for each one of those x values for any given point on that line. Now to better see how it's working, looking at something that's not a function is helpful. Alright, so let's consider the one on the right here. Now, if I go out to an x value, let's say I go to an x value of 3, and then I take that to the graph, I'm going to have a point here and a point here for an x value of 3. Each one of those x values corresponds to 2 different y values. In other words, for an x value of 3, I have 2 y values, 2 and -2. And so that's why it's not a function. Because for one input, I have 2 different outputs. And there's going to be a lot of that going on with that graph. As a matter of fact, the only point where that wouldn't be the case is the point 0, 0 is the only place on this graph where you have one input and one output. So this one in particular, if I asked you to explain why is this not a function, one of the things you could say is no, because 3 goes to 2 and -2, for example. So when you're looking at a graph, basically if you think about it, what's going to cause it to have more than one output is anything on this vertical value has an x value of 3. So anytime the graph hits that same vertical positioning, it's going to share an x value. Just like over here, if we were on this vertical positioning, those share an x value of 7, which means if the graph hits that x value more than once, then it's not going to be a function. So we could draw a graph in here that snakes around like this, you know, and I could just look at that real quickly and say, wait a minute, that's not a function because they're sharing multiple x values, several of them. As it snakes around like that, every time it hits the same vertical position, that's the same x value going to 2 different y values. This results in a common rule known as the vertical line test. The vertical line test says that if you can draw a vertical line through the graph anywhere and hit the graph more than one point, then the graph is not a function. And we saw that in the previous graph. So this gives you just a real quick visual check to know if a graph that you're looking at is a function or not. If it overlaps itself vertically, it's not a function. If it doesn't, it is. And I want to give you a word of caution. Let's say you have a graph here and it overlaps itself horizontally. For example, this here. Now here I could draw a horizontal line and hit my graph more than once. That's fine. That's still a function. As a matter of fact, we've called these guys quadratic functions. We know parabolas come from quadratic functions. So it's not that the graph overlaps itself. It's that it overlaps itself in the vertical direction. So as soon as it overlaps itself in the vertical direction, we've got one x value sharing multiple y values. In particular here, this x value corresponds to 3 different x values for points. 3 different y values for points on the graph. So hopefully you're seeing how this works out and how to see if it is a function or not. Go ahead and give some problems a try and see how you fare.